Okay, now we'll take a look at the interaction of 1s atomic orbitals in the formation of molecular orbitals in an H2 molecule. Beginning here for constructive interference. When we have two 1s atomic orbitals as such that are in the same phase, they're going to combine, and the overlap portion here is going to add up as we had demonstrated previously, resulting in a sigma 1s orbital. And recall what we said about the sigma bond. The sigma bond is going to be a covalent bond in which the highest electron density lies along the bond axis. Now, for the SS atomic orbital overlap, it's always going to be a sigma overlap. And you'll see that once you get more exposure to the SS orbital overlap. Now, the formed molecular orbital, the formed polycentric molecular orbital here is going to be delocalized over the entire molecule. And this lighter colored portion here just represents the dense negative charge in the center. Now, the orbital that is formed here, because it aids in bond formation, that's why it's known as the bonding molecular orbital. And recall what we had stated about the bonding molecular orbital. We had said that it's going to be, the bonding molecular orbital is going to be lower in energy than the two isolated 1s atomic orbitals that we have here, because its electrons spend most of their time in the region between the two nuclei, right, helping bond the atoms together. Thus, the bonding molecular orbital is more stable. Now, let's shift our focus to destructive interference. When we have two 1s atomic orbitals as such, and they're going to be out of phase, right, meaning one is in a positive phase while the other is in a negative phase, and when they combine, the overlap portion here, that's going to disappear, as we see here, resulting in a sigma star 1s orbital, or we can say an antibonding molecular orbital, because there is a node present, as you see here, with the nodal surface. And recall we had stated about nodes. Nodes are a region in an orbital where there is zero electron probability. And furthermore, moving on about antibonding molecular orbitals, we had stated that the antibonding molecular orbital is going to be higher in energy than the two isolated 1s atomic orbitals that we have here, because its electrons, they can't occupy that central region and they can't contribute to bonding. Thus, higher energy is needed to keep the nuclei in this unfavorable position, because the two nuclei are exposed to one another and there exists a strong repelling force between them. Now that we've taken a look at sigma 1s orbitals and sigma star 1s orbitals, let's take a look at the molecular orbital diagram for an H2 molecule. And that'll help us understand molecular orbital diagrams. Now, if we take a look here, we see that we have the atomic orbitals of for hydrogen, right? We have one here, and we have one here, and we have our the lower energy sigma orbital, and we have the higher energy sigma star or antibonding molecular orbital as such. Now, we have the filling of molecular orbitals is going to be exactly the same as it was for our atomic orbitals in accordance with the Apfel principle. Let's take a look at the first rule for the Apfel principle. That was orbitals with lower energy fill before orbitals with higher energy. Now, if we see here, we see that that's true as our sigma orbital fills before our sigma star orbital, right? Secondly, there may only be 2 electrons per orbital, and the 2 electrons in an orbital must have opposite spins. And as we see here, our sigma orbital complies, as we have 2 electrons per orbital, and they both have, as you see here, they have opposite spins. Next, we see here, when more than one degenerate orbital is available, the orbitals will half fill with electrons first, then the second electron will enter each of the orbitals. And we'll see an example of degenerate orbital filling once we revisit that O2 molecule. But for now, let's just go back and take a look at the bond order for just a moment. And recall we had stated about the bond order. We had said that the bond order tells us firstly if a chemical bond is going to occur, and secondly, how many bonds are formed within the molecule. Now, for our hydrogen molecule here, we said all we're going to need to do is take the number of bonding electrons, which is going to be 2, minus the number of antibonding electrons, which is going to be 0. And we see here that our bond order is going to be 1. Now, I have a question for you. If we recall, because the H2 molecule here has no unpaired electrons, is the H2 molecule going to be paramagnetic or diamagnetic? Well, if you had guessed diamagnetic, you're correct because there are no unpaired electrons. Thus, our molecule is going to be slightly repelled in a magnetic field. Next, let's take a look at an example where a chemical bond does not occur, so we can be able to differentiate the difference between between molecules. Now, for